So, this is similar to the first problem that we talked about, or that we had on the last homework. We're looking at, two copies of Z, Cartesian product of Z with itself. And I'm going to declare, well, here's the way that you add two things. You can actually add in here, because I have to tell you that part of B. We define the order pair AB plus CD to be A plus B, A plus C, comma B plus C. So you add them just like you add it to factors, right? I'm going to declare that AB is less than or equal to CD if and only if A is less than C, or in the case of a tie, B is less than or equal to D. And I stipulate that AB is strictly smaller than CD, if and only if AB is less than or equal to CD, but they're not equal to each other. We say that AB is positive if AB is bigger than 0, comma 0. Show that this is a total order. So what we're going to show here is partial ordering. I'm going to tell you what total ordering means. But total ordering means that everything's apples. If I pick any two elements, I can compare them. And here's something interesting. If I give you a real number, a positive real number, no matter what it is, 1/2 or 1/billion, and then another positive real number, would you agree that the small one, if you add it to itself enough times, it'll get bigger than the bigger number that I picked, right? This doesn't always happen. Show that there are positive elements bigger than 0, A, B, C, D, and C cross Z, such that for every natural number, no matter how many times you add AB to itself, it's still smaller than CD, right? And this is actually an important property of this kind of structure, and these actually come up in math. It's non-Archimedean in that sense. So you've got two positive numbers. No matter how many times you add this up, this one is still bigger. Number 2, suppose A comma less than or equal to is a full set. We define a relation, which I call funny little less than or equal to, by declaring that X is funny less than or equal to Y, if and only if Y is less than or equal to X. So basically, this is just reversing the order, right? This holds if Y is less than or equal to X. Prove the following. Prove that this is also a partially ordered set under this new relation. And show that this is well ordered if and only if this one has the property that every subset has a greatest element. Number 3, show that the non-negative real numbers equipped with the standard notation, the standard notion of less than or equal to is not a well-ordered set. I haven't told you what well-ordered technically is, but what a well-ordered set is it's a totally ordered set, so you can compare everything, and any non-empty subset has a smallest element. Number 4, let A be a non-empty set and PA be its power set. We're going to partially order the power set by inclusion. That is, UV are subsets of A. We say that U is less than or equal to B if and only if U is contained in B. We've done this. This is one of our first partial orderings. If XY is in PA, find the supremum of XY and the infimum of XY and justify your answer. You might be able, if you think about it for me, you might be able to guess what these two are. Number 5. In your book, or at least in the book that I recommended, and when I define it, a well-ordered set is defined to be a totally ordered set with the property that every subset has at least element. So well-ordered means it's totally ordered, it's partially ordered, and any two things can be compared, and it's got the additional groovy property that every non-empty subset has a smallest element. I should have said non-empty there actually, but for example, the natural numbers is a well-ordered set, right? Because we know that every subset of natural numbers that's not empty has at least element. Show that this definition that I give you is redundant by showing that any partially ordered set with a property that every non-empty subset has the least element is automatically totally ordered. So show that there's a redundancy in the definition. And finally, number six, show that a finite set is well ordered if and only if it is totally ordered. One direction will follow from the previous and the other one, you have to show. Okay, any questions on that? All right, well, let's get started then. Okay, so the last time we talked about the notion of what it means to be an upper bound, what it means to be a supremum, what it means to be a lower bound, and what it means to be an infimum, right? So let's open up with this theorem here. It'll probably help us in our understanding. Theorem 3,411. Let A be a poset. And be a subset of A. If supremum B or infimum B exists, then it is unique. Exists. Yeah. So what this says, we looked at some examples last time. We gave an example of a set, for example, that had no supremum, right? What this says is if a set does have a supremum, it must be unique. Okay. I'm going to prove this by assuming that if I have any two supremums of the set, then they must be. So suppose suit B this and so uh, what's this mean? What does it mean to be a supremum? Okay, it's an upper bound first, right? So X respectively Y has the property that X is, well, I'll do it this way. B is less than or equal to X for all B. Y, in other words, it's an upper bound. And respectively, B is less than or equal to Y. So for X and Y to both be supremums, then X is greater than or equal to everything in B, and Y is greater than or equal to everything in B, right? Well, what makes it a supremum? It's not just an upper bound. Let's also have the property that what? Small stuff around. Right. So let me be precise about this. Also, X respect to Y has property that X is less than or equal to U for all upper bounds U of B. So if anything is greater than or equal to everything in B, then X is less than or equal to U. But this is also true for Y. I agree. But y is an upper bound b. So by the first statement that I have over there, x is less than or equal to y. Right? Also, x is an upper bound. Okay. So y is less than or equal to x. Right? X is supposed to be a supremum, so it's less than or equal to every other upper bound, namely y. But y is also a supremum, so it's less than every other upper bound, namely x. So what can we conclude from this? That's right. X is less than or equal to y, and y is equal less than or equal to x. So y equals x by anti-symmetry. So there exists a unique upper bound. There exists a unique suit B. It exists. So there's no supremum, or there's only one. Notice that I only prove this for the supremum. I'll leave the infimum as a exercise because it proves almost exactly the same. Okay, any questions on that? Definition. And I think we saw some examples like this last time. So let me make this concrete here. Definition 3.4.12. Let A be person and be a subset. If the supremum of the set exists, and if the supremum of X exists and it's in B, we call X the greatest or maximal, I'll probably say maximum element. Notice this is how a supremum differs from a maximal element. You might have a supremum of a set that is not in the set, right? We saw some examples of this last time, where you have a supremum of B, so it's greater than or equal to everything in B, but it's an A but not B, right? That can happen. If B has a supremum and it's also in the thing, then actually the supremum is an element of B, and we call it the greatest element of B, because notice, since it's a supremum, it's greater than or equal to everything in set, and it's unique by the previous theorem, right? So there's one and only one maximal element if it exists. If y equals mb exists and y is in B, we call y the smallest or least or minimal element of So you might hear any of those terminologies here. Um, Notice we've seen some partially ordered sets where we had apples and oranges, right? We looked at the power set of 1, 2, 3, and we saw that there are some sets that can't be compared, right? So we also have seen sets where everything can be compared. So for example, the real numbers under standard less than or equal to the integers definition. These are the best kinds of partial orders. Let A be equals 7. We will declare that we say we say that the less than or equal to is a total ordering or a linear ordering if for all x, y, and a, we have x is less than or equal to y, or y is less than or equal to x. So in other words, this is the no apples no apples and oranges definition. This means if I pick two random elements out of my set, then one of them is less than or equal to the other. This is what you're used to in the integers and the rational numbers and the reals. If you pick any two things, one of them is less than or equal to the other. This is not true for subsets of the set, right? Because we've seen that you have, like even for the set 1, 2, 3, if you look at all the subsets, set consisting of just one and the set consisting of just two aren't comparable. Neither one of those contains together. In such a case, we say A is a total set. Definition. No. Let be a total set. Okay, so here I'm assuming right at the outset that my set is not just partially ordered, it's totally ordered. We say that the inequality is a well ordering or A is a well ordered set if every non-empty B in A any non-empty set has the property that B has a cell. So here's the hierarchy. Any well-ordered set is totally ordered. And any totally ordered set is partially ordered. The fact that a totally ordered set, the fact that a well-ordered set is totally ordered is by definition. But I asked you in the homework, I talked about this problem before class today, that actually, if you make this well-ordered assumption that any non-empty subset has a least element, that automatically gives you that it's totally ordered. So it's really not just by definition. And any totally ordered set is partially ordered. So let me, it might be good to me to throw some non-examples in here. But, so here's an old friend. Set of all subsets of the set of three elements. This is partially ordered. But not totally ordered. Because one is not contained in 2, 3, and 2, 3 is not contained in 1. So there's an apple and an orange that you can't compare. If I have this as standard less than or equal, let me give you the following sets. Integers, natural numbers, natural numbers, 0 union minus radical 2 I, 0 rational numbers, real numbers, and the set 1 e squared pi cube and 8675309. Okay. Which of these are totally ordered? All of them. All totally. Which one's the biggest one in a certain sense? The reals. Notice that every one of these is a subset of reals. Agreed? The reals are totally ordered under the standard less than or equal to, so any subset should be as well. Right? Which ones of these are well ordered, if any? This one's well ordered. In fact, we knew this, right? I mean, one of our kind of basic things, and it's equivalent to induction, is any non-empty subset of natural numbers has been still. What this one? This is also well ordered. And so is this. Any others? Why is this? Somebody give me an example of a subset of this that doesn't have a small settlement. How about the whole thing, right? The integers itself doesn't have a small settlement, right? So, okay, that was off the table. Well, these two have the same problem. There's no smallest rational number. There's no smallest real number. What about this one? Okay, so I see why Q fails, because Q has no smallest, there's no smallest rational number. What about this? What about the set of non-negative rational numbers? So I've gotten rid of the problem. I mean, certainly there's a smallest, would everybody agree there's a smallest non-negative rational number? So is this one well ordered? Actually, this one isn't either. Anybody give, this is a little tricky. Can anybody give me a subset of this that doesn't have a small settlement? Look at the subset of ones that are strictly positive. So just take this and throw out 0. Is there a smallest positive rational number? Take, for example, the rational numbers that are greater than pi, right? There's always a smaller one, isn't there? Because pi is irrational. Right? So this one's not well ordered either. But it is, of course, total. Totally ordered, but not well ordered. Okay. Any questions?
Oh, I was just wondering with the natural element or natural numbers, like what does that line mean? The union? Like.
Oh, so I took the natural numbers, I threw in 0, I threw in minus radical 2 and pi.
Okay,
So that's all I did there.
oh, okay,
But by the same principle as the natural numbers, any subset of this has a smaller cell. Okay, others? You know, I actually asked you about functions in homework, right? And one of the problems I had is, okay, well, I have this little C where I declare the two functions from the reals are equivalent or related. If their difference is continuous, right? And I appeal to your knowledge of calculus and functions from back then. Well, you Alex said in my office, vertical line test. Right. I mean, geometrically, you know, when you're doing that kind of calculus kind of thing, that's what you think about. We're going to see later why the vertical line test actually works. And of course, you can't do it if I have a function from this set into the set of triangles and circles. Good luck with the vertical line test there, because you can't really graph that well. You could, but it's difficult to think about vertical line test. Somebody tell me what they think a function is. Give me your best definition. Right, I mean, I put this in the problem on homework, see what I mean, guy, and depended on, you know, your knowledge from, say, calculus or pre-cal, maybe.
Is a function an operation which takes operates on elements of a domain and, that's unique. Right? Like,
That's about as good as it gets, right? That's what you get from your calculus, right? I've even heard of, it's a black box and you put in a number and it gives you a unique number. And sometimes students are a little bit puzzled about what's this unique number, and then you have to go back and explain, well, what's the square root of 25? Well, in calculus, that's why you find the square root function to always take the positive root, right? Because there are actually two things that square root of 25, 5 and -5. And your function has to make that decision on which one it is. Now, this is getting very sloppy. Would you agree with that? So, we're gonna talk about functions today. And gosh, I wish you could do this in pre-calculus, but pre-calculus is probably default, I think. But when you see this definition of function, yeah, it makes it much easier to handle. So functions, sequences, and their flavors, various types. Definition, so I'll jump right into this. Function. Uh, let's, function F from A to B, where A and B are sets. In the notation, as we mature with this, we use this. I think everybody has seen this notation before, have you not? At some point. Is a relation from A to B. Now, remind me, what's a relation from A to B? In its very most primitive form, a relation is a subset. Of A cross B. Right. Now, I'm not finished with the definition yet, but let me kind of help you develop language parallel. You all are used to this notation, right? Function of A and B. And here's the part that that Daniel was telling us about in the book, where you plug in something and it gives something, right? How is this a relation from A to B? Well, we think of this subset this way. Or A is related to B. This is how this relation works. Input A, get B. So I think of this ordered pair as the input, the output, right? And that's why it's a relation. And relations are easier to satisfy. So it is a subset of A cross B, but I've got a couple of rules. Number one, the domain of F is precisely A. What the domain of a relation is, it's everything that can appear as a left coordinate. Right? So what does this say? This means, here's a translation of what you're used to. You can plug in everything. right? So there is some AB. No matter what A is, it has a companion B. Now, there's that other strange thing about a function about, okay, every input has a unique output. It is now much easier to qualify that. So translation here, this means if I have the order pair x, y, f of x, y, f of x, z, that's what I mean in F, so it's in this relation, then what conclusion can I come to? Good. This is what a function is. This is beautiful, concise, clear, no questions asked definitions. What does it mean to be a function? It's a relation from A to B where the domain is all of A. So for every A, there's some companion B. There's an AB in there. And if X, Y, and XZ are both in the relation, the lines are the same. And there's your unique output. This is really, I think, easier to understand. Well, again, it would be harder for the pre-cal students because they haven't had the language yet. But if they had the language, this is much clearer and it's right on point. Let me do some follow-up here. Number one. So part of our language, if B equals A, then we say F is a function on A. So in the special case that it's a function to itself, this is all calculus, right? B and A are the real numbers, right? And two, B is called, you all are used to calling it the range, probably, right? It's where it goes. That's, I'm going to use a different terminology. Range is going to mean something else. B is called the codomain. So A is the domain, B is the codomain where it goes. Okay, so we've all seen functions, you know, the first example are familiar calculus functions. Well, I guess I should say this. In this function, the domain is R. What does it mean for an ordered pair to be in there? Well, it means your ordered pair is going to look like X comma sine X, whatever number sine X is. Notice that if X sine X equals X next, well, same problem there. What's the codomain of this? That is technically the way I wrote this. Codomain of F really. The range of F that. No, we're going to distinguish those. And in many cases that you where the distinction isn't important, but there are cases where the distinction is important, right? So basically, I could have also done this, right? Three, zero, union. Uh, which is what's stupid because minus 5 or whatever, right? This function here has a different codomain than the original one, right? But the range would be the same. Right? Now, if I wrote -1 to 1, then the range in the codomain would be exactly the same. Right? Okay. So here's an example. Let's look at, as I promised, how many of you heard of this vertical line test for a function, right? So this would be a calculus or pre-calculus, perhaps. Well, in fact, what do they even say? A graph is a function. I don't know, does anybody remember, what do they say? A blank or a curve is a function, or who knows, right? A graph or a curve is a function if every vertical line intersects the graph in at most one point. How many verticals? So you draw something and it's a function if every vertical line. We'll say a graph in the plane. How does this work? Well, let's suppose that you have something like this. Right? Now, my relation, actually, this is another good thing. Everybody, y'all can look at this and say, ooh, if I was taking calculus, this wouldn't be a function, right? I'll tell you what it is. It's a relation, right? This curve, whether it's a function or not, defines a relation, right? Because take any point on it, whatever it is, that's your x coordinate, and look at it's just put in the x and y coordinates. This is a relation. And the way I've drawn this, if this goes on forever, then this is a relation from, well, it's a subset of R cross R, right? So that's all we need. Now, suppose on the one hand that you have a vertical line that hits more than one point, like this. Now, you all can tell this intersects the 3 points, right? So what's in common, because this line is, well, supposedly vertical, this line, all 3 of those orange points have the same x coordinate, don't they? So we'll call this x, y, x, z, and x, t. Why is this not a function? Because notice that x, y, and x, z are in this relation. I'll call this R because this curve defines the relation. But y is not equal. So not a function. What I agree with. So what we've shown is if you can draw a vertical line through it and hit it in more than one point, it can't be a function, right? Because you violate this. Everybody agree? Now, on the other hand, what if it's not a function? Well, suppose relation R, from R to R, double say on R, is not a function. Well, either the domain is not precisely A, but I'll assume that the domain is all of R, because this is kind of a silly condition, because you can always change the domain, it's like change the codomain, right? So let's suppose that it's not a function because we violate the second one. Then there exists two different numbers, y and z in R, and x in R, such that xy, xz is in this relation, right? Everybody? Okay. Now I can graph any relation that I want just by inputting x coordinate and y coordinate, but already I've got this situation here. If I draw the plane and I'm going to graph my relation R, I know that for that value of x, wherever it is, there is an xy in the relation and an xz in the relation, where z and y are different. So I don't care what the rest of this looks like. It could be a circle, or since this is a relation, I can do all kinds of things. It could be like that. But all I need is those two orange points, bang. I could draw a vertical line through that relation. And so if it's not a function, then you've got that vertical line violation. Okay, any questions on that? Yes,
It seems sounds silly, but what's the difference between like the graph of the circle is like y equals x squared plus like z squared or whatever. Like, how is that not, like, I know it's not a function by definition, but what is it called then?
oh, well, so that's actually, I'm glad you brought that up. Let's explore that. So this is one of the first things is kind of, because a circle, geometrically and physically and everything, a circle is one of the most important things that you ever see in engineering, physics, science, math. So you're gonna get more departing from here, because I'm gonna also give you justifications of whole coordinates. Right, so this is. Right? And this is not a function, right? Here's the problem. This is why we had to do implicit differentiation, for example. You always have corresponding points like this, right? Everybody agree? So we've got this vertical line failure. Here's the problem. If I want to find the slope of the tangent to this, say here, right? Well, what happens when I plug in x to whatever I get from the derivative here? Well, now you've got to make a decision. This is not really a function because for every point x, well, except for these degenerate ones right at the end, but every point x, there's actually two values here, right? And the problem is, yes, you can make it a function, but you do it this way. So if you're doing calculus on the upper half of the circle, that's your function. If you happen to be doing calculus on the lower half of the function or the circle, that's what you do. Right? And that's one of the things about implicit differentiation that worked out well, because what you did is you took the derivative of this without solving that square root. But then when you do implicit differentiation, what happens is you actually have both an x and a y in your formula for the differentiation. And the y coordinate is when you're making that choice. Am I picking the upper circle or the lower circle? Right? What does this look like in polar. What's the radius of that circle? It's r, right? In polar. I really, we'll do our thing as a standard. We consider theta to be a dependent variable. Or depend on, this is r equals 1. No, it's not. It's r equals r, where the radius of the circle is r. This is actually a function. This actually passes the vertical line test. Oh, see why? Because now I'm not going here for vertical lines. I'm going by theta, right? And each value of theta, if I just do one direction here, only hits that in one place. That's why polar coordinates, it's easier to do things that look like circles, because you turn this complicated thing actually into a, in fact, circles are the analog and polar of what horizontal lines are in Cartesian, right? Horizontal lines, you get y equals constant. When you have r equals constant, you get the circles. So it turns doing calculus problems in Cartesian on circles is hard into something that's easy on the circles, right? Unfortunately, in polar, if you try to do stuff with lines, it's a huge pain. So there's tit for tat in that. But anyway, that's a good question.
Is it just called like a formula? Or like, what is this? Like, is it just called a formula? It's not.
Oh, I'd call it a relation.
Oh, just.
Yeah, I'd call it
okay.
a relation. Yeah. Okay. Others? Yes. What's that now?
Aren't you getting multiple,
Yes, you are. So it's not 1-to-1, right? Because, for example, this might be theta is power 4, you get the value 1. It can be, theta is, power 4 plus 2, 9 power 4, and also get theta 1 12. Yes.
When they were, this might be a dumb question, but when they were like coming up with all this, like, what's so special about it, having that unique property? Like, why did they care so much?
Because if you're doing stuff with math like on the circle, if you don't have the unique property, you have to make a choice, right? So let me give you a quick example. If I have a parabola, which is a function, and I ask, what is the tangent line to this function at the point 1, 1, or when x equals 1, tangent line? There's no ambiguity. This is the point you're looking at, period. If, for example, this is x equals a, and I say, what's the tangent line at x equals a? Now you got to go further and make a choice. And of course, there are ways to deal with that. When you're in calculus, you do parametric equations as well, right? Which many of those are not functions, but you have a function in x and a function in y, and you can get around things that way. So does that answer your question? All right. Yes.
in polar, isn't the domain order the theta?
Yeah, but this is the standard way that you represent it. This is usually considered the independent variable. It's the deepest.
So
So it's like yx.
for a function, there has to be a unique, for every like value in there will be value.
Mhm.
So for the circle, it's not hold.
No, it holds, right? Because this is the independent variable. This is the domain. And the unique value is r, right? No matter what theta is, you get r, right? So it's just like, that's it. I mean, you might be confusing 1-to-1 with this, right? Because given any input theta, there's only one outcome. It's r.
Okay.
Right.
Okay, so theta's the
Theta is the domain. It's the independent variable. R is the dependent variable. It's the codomain. Yeah, I know. I only wrote that way because that's the standard notation, but it is confusing because you're flipping the usual roles. Oh, math club today. It's about lean. How many of you have heard lean? I probably shouldn't tell you about this math club because lean is actually a computer. It's a computer programming language that's a proof assistant, right? And it's actually fairly new. It might be kind of a way of the future. It should be an interesting talk. So I recommend it if you've got the time, 5 o'clock, right across there. Otherwise, y'all have a good week.